Hi everyone, my name's Abby and I head up the business development for ArcticDB. Firstly, it's fantastic to see that so many of you signed up and attended. So please do feel free to reach out to me after the webinar if you're interested in discussing more about your use cases. I'll be here in the background to help field some of your questions and answer over Q&A. And with that, I'll hand back to James and I'll disappear into the background.
Yeah, thanks. Abby's going to be helping if anything goes wrong. Hi everybody, I'm James Munro, and I think we'll get going. As Abby says, we've had a really good response to this. So pleased to see hundreds of people sign up, and a lot of them have joined already. So we'll get going. I run ArcticDB. And I'm going to give you a little bit of an intro and the whys and wherefores of ArcticDB, what it's all about, and then we're going to do a demo as well. Do ask questions. I think we've got time that I'll be able to pick up questions as we go. There is a bit of a delay, I think, in practice between when I say things and I change slides and you see them. So I might pick up a question after I've moved on from it and go back. We'll just have to see how that goes. Yeah, let's get going. So just to introduce myself a little bit, I've been working in finance and quant development for about 13, 14 years at Man Group. And before that, I was a physicist. And now at Man Group, I've moved on from that pure quant dev role and running tech teams. And I used to run AHL technology at Man Group. And now I'm running ArcticDB. And we're making ArcticDB a product and a business and making it available to everyone publicly. And this has been the last year for me and Abby and others. So we'll tell you a bit about that. So first of all, just to tell you about our origin and how much ArcticDB is used by Man Group and how that came about. So Man Group is a very large alternative asset manager, $178 billion under management as of mid-year, several hundred clients. We've been doing this asset management gig for about 35 years. In fact, Man's a very old company, founded in 1783, but moved to asset management 35 years ago. And we run all sorts of styles of things, and this is important for the Arctic story. So we're running macro funds, quant systematic funds, discretionary funds, long-only stuff, multi-strategy stuff. And so we've got a whole bunch of use cases internally. And all of that is supported by a single technology operating and data platform. And all of the data in the front office is worked on in ArcticDB. And so for us, that's been incredibly valuable first user, if you like, because for one thing, it's operating at scale. So Man Group trades an awful lot. It's an active manager. So, if you've got several fold leverage on that $178 billion from the fact you're running leveraged funds, you've also got several fold more trading going on from $1 trillion to say 6 trillion because you're trading actively. We're using data all the time to decide whether to be long or short markets, whether you're a PM or whether you're doing this algorithmically. And we're using that to decide how to trade every day, and it's all very active. So there's lots of trading going on lots of markets. And we have all these styles, as I've mentioned. So this kind of scale has meant that now we've got petabytes of data in ArcticDB and Man and elsewhere now. And we've got several hundred users there who've tried to use it for everything imaginable. So it was a great first use case. And then me personally, running AHL technology, the biggest users of ArcticDB, and now I'm actually running ArcticDB and owning it. So to see that to move from be the biggest user to be the owner of the platform has been kind of interesting for me as well. So the story is actually over a decade old, and I'm going to go into the whys and wherefores, but we had a first version we open source, which was purely in Python, which we've built to kind of get more agile with data and more performant with data. And it's been well used, but we've continued to develop that. We've now got something that's written almost entirely in C++, Its performance is truly world-class. A lot of people say that, but I'm going to prove it with some demos today. And we're running it enormous scale. We have tens of thousands of cores of compute running against ArcticDB within Man and within other asset managers and data providers. And as I've mentioned, it's used in anger, so in production and in research, and across all our asset classes and data and across others. So that's the story. One thing I think it's always useful to mention is like the whys. So why build a database, right? Because there's thousands of database technologies out there, and surely one of them fits your use case. I think that, you know, at some level, it can seem a bit crazy, this idea, or that you're going to do this. You know, you just need to find the right thing. And so it reminded me of this quote, which I've got this DALL-E image for. You know, the distance between insanity and genius is measured only by success. So, this is by Bruce Furstein in this quote, and he's an American author. And so is it genius or is it insanity? I think it's actually reasonable because, you know, this is not unique endeavor in finance. There's a number of large asset managers who've come up with their own data technologies for good reason. All the major tier one banks have proprietary tick and, you know, chunk databases for good reasons. And a lot of these reasons are shared with the kind of ArcticDB reasons. And, you know, no database technology is born in a vacuum. We're all born to serve a purpose, and we're all born out of the needs of a business. So that's what it's been about for us. So the particular whys, if you like, are these for me, that quant productivity that we need, the agility with data. And by the way, I'm going to talk a lot about quant, but I think a lot of these lessons apply to data science in general. Being really good and agile with data, so a really easy to run flexible system. I'm going to try and explain what a data frame value chain is, why, you know, we think of data frames first, not individual pieces of data. And some of the real world issues with working with data and why we've designed ArcticDB to address those. And then performance, I'm not going to try and explain that, I'm just going to do that with a demo. I like to explain the research productivity by an example. And by the way, do ask questions as we go. I know I'm not getting into the technicals quite yet, but I'm sure you'll have some. So I like to describe this kind of research productivity challenge with an example. So this is a plot from an economic paper by Bloom, Jones, Van Reenen, and Webb in 2020. And they go into like research productivity across US markets. And they've got this nice plot for Moore's law. We probably all know Moore's law, that the you know, semiconductor density has been doubling every couple of years. But with that growth rate has been this kind of research productivity challenge. What was one researcher in 1971 is now like about 18 researchers in 2014. So this, like, the cost of that progress has been going up, and that works in like an exponential space, like computing has been. But that doesn't, you know, always work, that you can afford to pay that research and development cost. Now, I haven't got a plot that explains this for quant, but I think it's a very similar challenge because you know, there's tremendous competition. Data challenges in the quant space have just been climbing and climbing and climbing. You've got not just the like volume of tick data, you've got like diversity of data and all this kind of alt data use cases now. And you've also got like this drive for efficient markets and new asset classes. So it just gets more and more complicated to be at the forefront of this game. So by analogy, I'm saying quant productivity is probably the most important problem we work on where we are. So another part of the why has been about like the process of asset management for ArcticDB. So for data and ArcticDB, and like at a high level, the the value chain of any asset manager is this, like, or any individual is this, even if you're like picking stocks yourself. You know, you're collecting data, you're generating ideas, you're deciding how to trade them, whether that's discretionary or like algorithmic, systematic. You're coming up with some portfolio trade optimizations, and then you're deciding and going to the market. So this is kind of like the process for everyone, whether you like it or not. But the reality is, in like 2024, that this has become an incredibly complicated space. So data is just incredibly complicated and vast now. Statistical methods are becoming more and more sophisticated. You know, you might still be doing linear regressions, but now you're looking at how ChatGPT can add value for you. I talked about the number of funds that Man Group runs and the number of amount of portfolio construction we therefore have to do, the amount of risk analysis that you have to do, and all of the work around the analytics of trading that you need to do efficiently. So all of this has become incredibly complicated. So you need like a really agile tool to serve all these use cases. Next slide is about like how data frames have become ubiquitous in systematic trading. So this is not just a story about this asset manager, but I think it's been a wider story. Definitely talking to peers in the industry, they talk about a similar transformation. And you know, almost every sophisticated systematic asset manager, so where you're doing algorithms and models to do your trading, are going to have this kind of Lambda architecture. A Lambda architecture, from my point of view, is like an architecture for the ages, where you've got some data problem and you've got two kind of basic formats of data coming in. You've got streaming data, high frequency data, and you've also got like batch data, alternative data, fundamental data. And so it's very natural to split your pipeline in two based on that, because they require they've got different needs. So tick data's coming in, and then you're storing that, you're archiving that in its rawest form. You're also generating like lower frequency views of this, typically 1 minute bars. That's very popular. And then on your fundamental alternative data side, you've got much more of a data lake architecture, and you've got some sort of catalog for looking at all the data sets. You might have thousands of data sets. And then these things are feeding your strategy, your model for how to trade your markets. And in there, you've got your risk management, simulation, back testing, trade, and portfolio optimization. And all of this stuff has become stuff where you're working with data frames. And now for a lot of businesses, not all of them, but a lot of businesses, people have gone with Python for this in the modern era. So that's where ArcticDB fits. And although you might go to trading and then you're back into your low latency messaging systems and probably your transactional databases, at the end of the day, you're going to want to do analytics on that trading, and then back into a really convenient format for doing analytics and trade cost analysis and things. So yeah, just to explain, so let's look at some of the challenges with working with data. I'm going to use bonds for this example. I think it's interesting because it's like a bigger space than equities in some sense, right? In terms of notional amounts in 2021, according to Wikipedia, it was $120 trillion of outstanding bonds, and market size was 3 times that of equities globally. And there's actually a sort of skew towards the US for trading bonds. So a lot of the market is in the US. This has been like fertile ground for quant, as of like a market to get better at and more systematic in over the last 5-10 years. And the data is more complicated, and the analytics ends up being more complicated, and the data ends up being wider. I'll come into that. And so this is a great example data set for ArcticDB. Let's have a look at it. This is plotting out pandas data frames in Python, and how you might manipulate the data. So if I look at the top, that's typically how data comes in, and we store it like this as well. You've got a very normalized table, dates on the left, you've got IDs for your assets, and you've got prices, you've got other measures as well. So here there's 44 columns, and on the right, we've got durations for the bonds. So this is, often how we're all getting data in finance. Now, the reality is it's not the most useful way to work with this data often. And I'm not saying there's one view of the data which works, but I'm saying you need other views and you need those other views to be performant. So if you want, for instance, to look at all of the price data for all your historically traded bonds from this provider, so this ICE, BAML, and market data, then there's actually 430,000 of them. And it's sparse, right? There's bonds that haven't been issued yet, and there's bonds that have expired, so it's ragged data. And so you need a database that kind of helps you work with this way. And I've got it in the demo later. I can explain why this cross-sectional kind of view of a single measure becomes a really powerful tool for people wanting to do analytics on, whole universes of assets at the same time. And then you need the right tools for this. So this is going to be, many gigabytes of data as a whole data set. This is the tail of the data, but there's a few thousand rows and like 500,000 columns here. So it's more than would fit on this laptop. So you want to be able to slice and dice this data easily. So really here we're talking about the normalization trade-offs of data. As engineers, we get trained to kind of normalize data nicely. But as users, we want things in different formats. And another way that we typically want to work with things in finance is by ticker. So in ArcticDB parlance, these are symbols. And you want say, for instance, your measure to be continuous, and you want the whole time series. And you either want all the measures or you want the measures across everything. And so these are the kind of views that we build, and these are the kind of views we've optimized ArcticDB for. And what this means is that, yeah, we need something that works really well with really long tables, but also, as I've said, really wide tables. But there's a second important point here is that you want something that works without it being fully normalized. So this is the less normalized view where you've got ragged data, you've got stuff that disappears. You also need schema evolution in your table, right? You need to add columns as you go because new bonds are issued, or you've decided to create new strategies or new funds or whatever it may be, new factor models. So you're adding columns as you go, and you're dealing with and working efficiently with potentially sparse data. Okay, I'm going to go to the demo already. And as with any demo, there's some risk. So wish me luck, hopefully. So first, I'm actually going to run in one of the nice things about ArcticDB is the number of storage backends we can support. So typically people are using S3. We also support on disk format. We're kind of working on Mongo and getting that out. And then we also support kind of S3-like systems like Azure Blob Storage. So I'm running this in Azure Machine Learning Studio, but other clouds are available. And just to give you a flavor of the size of this, so we've got a 32-core machine. So it's a decently sized virtual machine here with 256 gigabytes of RAM. You don't need to do this kind of demo. So I'm just going to import ArcticDB. And then discuss a few of the concepts so the rest of the code makes sense. So we've got our account level here. We've got the storage bucket here in Azure. And then inside those storage buckets, you can have thousands of libraries. So we've got something like, 30, 40,000 separate libraries in Man Group. And each of those is kind of conceptually a data set, something you want to work with. And as a user, you may have hundreds for yourself. And if you're providing, market data, you might split it into region and asset class. And then each table is called a symbol. And this is just to be like an example, but you might decide to store things by asset ID, for instance, and that would be logically quite simple for people. And then each table is versioned. So one of the features of ArcticDB I'll go through is this whole time travel feature and the point in time aspects. So a few noddy data frames just to get started. This is just normal pandas. So we've got a little data frame of 1s, a little data frame of 2s, and a little data frame of 3s. Okay. And then I'm going to connect to this Azure backend. I'm loading my secret password to connect to this, and this is the standard Azure connection string. And I'm listing the libraries. And here, so for the demos, I've got 3 data sets. This intro data set I'm using in this notebook. I've got one that shows downsampling, and I've got one that shows some example US equity data. So I'm going to load that intro notebook, data set library. And then you just write and read data as whole data frames, typically. So there we go. And it tells you what it did. And this is version 6. So I've run this notebook a few times before. And I can read that back out. So this is really like the basics of ArcticDB. You modify data frames, and this is really built for scale. So if you want to be doing this with thousands of rows. So I'm going to append just my data frame of 2s here, and I'm going to read it back out again. And now we've got the data frame of 1s connected to the data frame of 2s. So you can append. So this is like, and this is producing new versions. You can modify the middle, and this is not just about time series. You can store any kind of data frame in Arctic. So here I'm putting 3s and with an update, and it's done it on the index into the middle. So I've got 1s, 3s, and 2s. So this just to sort of give you a sense of the basic simple operations of ArcticDB. And as I said, it's like got this time travel feature. So I'm going to go back to that initial version, which was version 6, read it back out again, and it's still there. And all these versions are cheap. They just store the deltas. So those are the noddy examples. Let's try something a little bit bigger. So I've got here something with 100,000 rows and 100,000 columns. Oh, there we go. So I'm just going to pluck some of those out just to show that you can slice and dice this data. So I'm pulling out 6 columns, arbitrary columns, and a few days of data. And there we go. So you can just pluck data out of very large data sets that wouldn't fit into RAM. And in this way, you can parallelize your job if you need to, or run your jobs in a for loop. So it really scales to the kind of workload you want. We're used to very much people using it in Spark and Dask and things like this for parallel compute. That's a very wide, scroll back momentarily, that was a very wide table. We're good at tick data, so let's look at a very long table. There's 100 million rows. So I'm actually going to write this live. Oh, I didn't import time. There you go. This is the risk of doing demos. You'll see how long it takes. Come on, laptop. There you go. So that was about a second to write 100 million rows. So I'm going to stop that and actually go over to another demo now. We're going to come back and do a little bit of downsampling. So I wanted to kind of get across, I tried to do that with the bond example, but I wanted to really get across the value of having wide views and having these. So here we go. This is one where we're going to look at some US equity data. So connecting to the Azure storage again. Let's have a look at the US equities library, list of symbols. So here I've got total capital, total assets, shares outstanding, volume, adjusted price, and an estimate of number of employees in each company. And this is all US equities, okay? And in reality, you might do this, you might have hundreds of measures for US equities. So let's look at the adjusted. So here I'm just going to get a description of this data frame for the adjusted price. And I'm pulling out the column names and just looking at a few. So these are the asset IDs. I think these are TQA IDs or RICs. We've got 27,000 of them in the universe that we've subscribed to. So let's load the adjusted price. Think of this as total return, really. One moment. So here I've loaded adjusted price there extremely quickly in less than a second. That was the whole universe for all time. And I'm showing you the tail of that. You can see it's sparse here. Lots of assets have gone away. This is the bottom of it, right? But some are still around. And this is the first few columns and the last few columns. Okay, so you've got something like that, and suddenly I can now look at the whole US universe, and here I'm going to calculate 1 week returns. So I'm going to resample to 7 days. This is just pandas now. Aggregate on the last, so it'll get the last price in 7 days. Take the percent change times by 100, and do the weekly standard deviation now. So this is weekly vol. Pandas takes a few seconds. There we go. And then let's plot that, see what it looks like as a histogram. So just like going from now, if you're creating those views for yourself, going from those views with a database like ArcticDB immediately gives you kind of useful results. And you can see there were like amazing spectrum of volatility on US stocks. I've got another example here with employees. So this is reading the employee estimates out. And here it is a bit noddy. I'm taking the mean across the column. So this is the mean overall time for each stock. And at least where it's non-NaN, so where it exists. And I'm sorting that. And then I'm going to show you the original table here, employee estimates. So here, this company had 27 employees, and then it went to 617. But I've got the means available now as well. Okay, so let's plot that. There you go. So now I'm looking at the distribution and number of employees on average over all time. There's some ridiculously huge employers in the US. Okay, so surely this is related to the capital of a stock somehow, right? So let's read out, again, I'm taking the mean for the capital, a little bit noddy, but let's plot, let's plot capital against employees across US stocks. So that was the calculate, I was just producing the table, and this is the plot. So you see capital on the left, and number of employees on the bottom. So it's just like ludicrously easy to work with this data and do analysis across your whole universe when you can get the data out in the right format quickly. You can see a kind of nice feature here is that some of these companies, and you can definitely see there are errors in the data, but some of these companies have 1, 2, or 3 employees, but they have large amounts of capital. So you can imagine these are shell companies. And then these big blob is like usual companies. So that's kind of the demo of wide views. So I'll finish the demos with a performance demo. So this is running in the cloud using this 32-core VM. I'm competing with everyone else in London in Azure, in Microsoft data center for space and time. So let's do something a little bit more controlled. I'm going to run something on-prem. This is much more of a low latency setup. So there, I'm connected here in a notebook to a local development machine. It's actually a shared machine. And I'm going to give you 2 storage backend examples. So we've got LMDB, which is our local file system format. So this is going to be the most performant that's connected locally to an SSD. And then I'm also going to connect to a local on-prem S3 storage, which is close by to this machine I'm running. And so I'll load those 2 up. And then the box I'm running on has got 2 32-core processors. So it's nothing actually, like it's not like a ridiculously large box. This is like something you can typically would buy in a data center these days to do work. And this is a shared development machine for ArcticDB. It's got 500 gigs of RAM. Again, you can get machines with terabytes of RAM, so it's not ludicrous. There's no GPUs on this machine. It's running a couple of years old Ubuntu, although it's under long-term support and is patched. It's a development build of ArcticDB, so it's a little bit special. So this is not out on our last release yet, but it's our V2 encoding. And we are running simulated tick data, so it's nanosecond timestamps, 30 millisecond intervals. The prices are truly random, but they're slowly varying, like normal tick data would be. And the volumes are random small ints, like normal tick data would be. So let's do a read of that data. So I've got quite a few ticks in the simulated tick database. So if you look down here, that is just over 1 billion rows. and you can see the top and the tail of that data. It's just 2 columns, but that came back in 1 second. So ArcticDB can do 1 billion rows a second, and there's just nothing out there else out there that can do that into a Python process. And then to show you what it looked like over a network, which might be more of the shared data example, so not if you're working individually, but if you're working with a team, and the cost of doing things over a network. So this is the same data, precisely the same data, and it's 1 billion rows, 2 columns, 4 seconds. So this is doing 250 million rows per second across the network into Python pandas data frame, just a normal pandas data frame. Now that's quite a challenge to work with. That's a 24 gigabyte data frame there. So it's important that you can like slice out this data and work with it in pieces, and that's an important tick data use case. So here I'm pulling out 1 day's data using this date range argument, and I'm just going to pull out the last column. Oh, I didn't run the cell before. So in 80 milliseconds, returning 2.8 million rows. So it's like with this sort of technology, like the problem becomes how fast you can do things in pandas and polars, not how fast you read the data. And let's show you some downsampling. So it's a new feature for us. It's coming out in the next release, actually. And here I'm going to resample. There's lots of parts of this, but I'm just going to do a really simple example on where I resample to 1 minute boundaries. So I'm going to reduce 1 minute bars, and I'm going to take the last column and do the mean over the minute. So it's actually doing a calculation. Typically, you would produce a more complicated 1 minute bars than this, because you might want all sorts of measures from your normalized tick data. So how long is this going to take? So 124 milliseconds. That's actually a little bit slow. 100 milliseconds. So that was doing the same date range. So that's doing the same day of data that's here. So it's downsampling that 2.8 million rows into minute bars in 100 milliseconds. And now you've got something you can actually reasonably plot without breaking your notebook. So there you go. That's the simulated ticks for that 1 day. So those are the demos. So how does it achieve this? So, and here's our polar bear mascot trying to find his way through a complicated set of technology constraints. So there's various layers to this. A big part of it is this immutable data structure that we use, and we're storing objects in S3 or Mongo or on local file systems. And so each data frame, so this is the kind of data structure at a high level for each data frame. And you've got a named data frame here, Apple, connecting to some version of that data frame. And all these versions are making a kind of like new references to these data frames. So the old versions exist in a chain, we call the version chain. And there's a lot of indexing of all the different segments. And these data segments here are compressed columnar format, which I could have several slides on about how we're doing that. And then these data segments are actually shared between versions. So version 5, if you only added one chunk of data, version 5 will share its link to the data layer. So that's how we get efficiency in versions. And if you want to have a look at William Diltrey, who's our chief engineer, have a look at his Medium article, you get a bit more depth from that. So one thing is that like the value of keeping these versions. So there's another question about tracking versions and different versions. So it's really been important for the users that they can, particularly for like point-in-time data sets. And not every data set needs to be point-in-time. Typically, tick data, you've got some kind of, good timestamp, although you do care about other timestamps. Often with tick data, you care about a lot of timestamps. So you want multiple timestamps. But particularly for things like, I don't know, estimates, like I had estimates of employee counts on stocks, like that stuff needs to be point in time, or forecasts, that stuff needs to be point in time. So it's been a very useful feature for our users, whether it's looking at the changes in the data or the changes in their outputs. And this is also kind of really important for doing data science, that you're able to understand the changes in your model. So if you change your model or rerun your model, how have the inputs changed and how does that relate to the outputs changing? So that has been like not only a key part of getting the performance and the scalability right for ArcticDB, but for a key part for the users. So apart from data structures and the compressed columnar formats, we've got this kind of unique system where there's no database server. So on the left here, I've got like how most people are doing things at the moment. You've got some sort of storage layer. It could be local SSDs inside these database servers, or it could be some shared storage. More and more common these days that some sort of shared storage, like S3. That's how like Delta Lake and things work. And these database servers are doing the execution and the optimization and the indexing and the job queues if there's too much contention. And the users are working on these, and you need to scale kind of like your database servers to your user load. So, and a nice way to think about this, I think, is that you're splitting up your concerns, according to the API. Your database servers are managing the security and the execution, transactions, indexing. And then there's a split of responsibility for the capacity and resiliency between your storage and your database servers. ArcticDB makes it effectively a different set of choices. There's no database servers. Because we're using these immutable data structures, shared data structures, we're able to work on the data independently. There is a limitation to that. You have to give up on your isolation. So transactions divide themselves into these kind of 4 requirements, typically called the ACID requirements: atomicity, consistency, isolation, and durability. You definitely need the other 3, atomicity, like things happen or they don't. There's no middle halfway house. You want consistency. When someone's finished writing, you want it to be available. You don't want things which are invariant and are supposed to be invariant in a database looking wrong. And you definitely need durability, and systems like S3 offer world-class durability. But isolation is something you can give up, and it just gives you so much like power and scalability when you give it up, and so it opens up so much performance. And that's the idea, that you need to like coordinate access or writing to a data frame. So ArcticDB doesn't promise, for instance, serializability. So if one person writes and then another person writes to the same data frame, then it's possible that the initial write is forgotten. But that's actually really easy to give up when you're in this world of like so many data frames and having data sets full of data frames, and because there's an ownership here, and you can decide to update one asset from one writer. And beyond that, we actually have features to support consistently writing to a single data frame from multiple places. So if you look in our documentation, it's called staged writes, and it allows you to run a second task, basically, to coalesce the inputs and produce a single data frame. So it's not much of a cost for a huge advance in your ability to scale. And the other kind of aspect of this is you're doing a whole bunch of work in your users' nodes, Python processes, and that's actually a nice feature, right? So because I'm doing data science, I've got my users, I'm doing it on a machine, and all your database logic is happening there as well, and that's scaling with the kind of scale of your data science that you're doing. So you've got a very naturally scaling database, and when no jobs are running, there's no compute running for this, right? All the data is just at rest, being incredibly cheap. And finally, we've not had to work with security or capacity or resiliency stuff, because it's all handled by the storage layers. And these are the same kind of storage layers that are used to run like Netflix, right? These things work at internet scale. And then, despite this kind of choice in architecture, we've got something that's and because of this choice in architecture, even we've got something that's incredibly simple to set up, like AWS. So you install ArcticDB as a client library. There's no server side to install. You create a bucket in EG AWS. Other clouds are available. So AWS S3 make bucket. And then you configure your credentials, and that's it. You've not only got something you might use personally as like your infinitely scalable data store that doesn't cost you anything when you're not running anything. You've also got something you can run as an organization with thousands of data sets, millions of data frames per data set. And it's just as easy to connect to as a normal database with a password and a URL. And it's got this really nice, easy to use data frame based kind of pandas-like API. And then on top of that, because of the data structures we had to choose to make that possible, we got this time travel feature, which has just been a massive win as well. So, you know, I don't want to oversell it, but it's been pretty fun to work on this. I showed the billion rows per second. This is a snapshot from our storage device, which is a picture on the right there, which is an on-prem S3 device, the same one I was reading from in the demo. And here we're reading out 40, potentially 50 gigabytes per second. And now some of these numbers, unless you're used to working with them, it might be like, is that a lot? Well, actually, like a fast data connection in a data center these days is like 40 gigabit E-links. So that's 40 gigabits per second. So if you want to do 40 gigabytes per second, you need 8 of those links. So actually, this is like and anyone who does real networking knows you can't actually do that amount of work with 8 40 gig E-links. So here we're actually saturating more than 40 very fast network connections into that bunch of SSDs on the right. And that is all without any database servers, and that's serving up to Python processing across a very large Spark compute cluster internally. Okay, so all of that I've gone through is free, basically, as a hobbyist, as a personal user, as an academic. Love you to reach out. We do have a restriction in our license against production use. So we'd like you to respect that, please, and reach out if you'd like to use it in production. But we've been providing community support, and the support source is available on GitHub, and you can just download it and try it. It's as simple as pip install or on Conda as well, if you like Conda. Beyond that, there's a bunch of tools I've not showed yet. We have pro tools, licenses for production use. We give dedicated support, enterprise tools around things like replication and backups, if you need that in the cloud or on-prem, and we have streaming data collectors for things like tick data and consultancy and SLAs. So that's what the business is about for ArcticDB. And definitely love you all to follow up separately. Let us know what you thought of this webinar. Have a look at our website, try it out. There's a QR code there, which is for the GitHub page. I'd love a GitHub star as well if you've got a GitHub account. And with that, we're kind of coming to the end, and this is where I'm going to ask if Abby can let me know if I've forgotten anything critical, and I'll show a compliance page. And if you want more details on for the compliance as an asset manager, we can let you know afterwards as well.